And the first thing that she noticed is that there was a strong coordination on the starting material, not only between the lithium and the triple bond as expected, but also between the lithium and one of the oxygen of the acetal. Very strong chelation, very strong coordination. This is very favorable because, of course, it puts the two carbons that have to react together in close proximity through space, right? So that's a favorable conformation. And indeed, when the reaction starts, you see that the triple bond here is bending, but it's bending in a very strange way because it's bending in a pro-E way. You see that? You see here the triple bond. It doesn't look like a triple bond anymore. It looks like a double bond already. But the distance is still a triple bond. It's a 1.2 angstrom carbon-carbon. So it's still a triple bond, very bent, but it looks like a E double bond. And this is due to the persistence of the chelation between the lithium and the oxygen. So this interaction bends the triple bond the reverse way. And because of the persisting interaction, the double bond which is being formed will take the E configuration and not the expected Z one. So this explains the very strong influence of the acetal moiety on the course of this reaction. So let's see what happens next. Next, of course, the carbon-carbon bond forms here. The lithium is still here. You see, it didn't move. And the double bond, the doublet now, the charge is on the other side. So the lithium has to move from here to here. And it rotates, carried by the oxygen of the acetal, like a crane. You know, the crane of the acetal is carrying the lithium from this side to the other side to deliver it where it is needed. So it's a crane-like rotation of the etoxy group. And so the etoxy delivers the lithium. And finally, the lithium ends up at the good position here. But you see that the interaction with the oxygen is still very strong. So all along, the oxygen-lithium interaction is very strong, and that explains the very unexpected course of this reaction. So you see that the lithium turning with the oxygen. So this persistence can explain the E-selectivity. All right, so this is, of course, just the kinetic aspect. What about the thermodynamic aspect? Well, nothing wrong with the thermodynamic aspect. This is the course of the reaction as expected. This is the starting material with the phenyl lithium compound. This is the transition state. It's an early transition state, so it doesn't change much. Slight deformation of the triple bond. And then the reaction takes place. Strongly exothermic reaction, minus 45.6 kilocalories per mole. And then the cyclization is obtained with the E double bond as expected. And you see that the barrier, the activation barrier, is only 8 kilocalories per mole, which is very low, sufficiently low at least to be a quick reaction, minus 78 degrees. What happens with allenes? Because you remember that allenes were very good also in this chemistry. Why do allene functions very well? It's just because if you look at the starting point, you will see that there is no possibility this time of chelation between the oxygen and the lithium. And as you can see now, this is the starting point. You see this is the lithium. No interaction with the acetal. The acetal is very far away because of the linear aspect of the allene. Impossible to get an interaction. So the lithium now is standing alone. And you'll see that for the reaction to take place, a rotation around the oxygen carbon here must take place, such that there is a strong interaction between the central carbon and the lithium. And you will see that there is a bending of the double bonds here. Now the lithium is interacting with this carbon, and the reaction is ready to start. So it goes very fast. The cyclization is taking place. Very little activation barrier, 2.5 kilocalories per mole, almost nothing, very fast reaction. And then you obtain this intermediate that is ready for beta elimination, a very simple beta elimination, since this carbon is sp3, only less than 1 kilocalories per mole, and you obtain the expected compound. So it explains that with allenes, everything goes well, not only the cyclization, but also beta elimination. So this reaction becomes very favorable with allenes. Oh, these are the intermediates just to show you what they look like, and this is the final product. Okay, so the second question remains is, why do we need an excess of base to do the elimination when we are using an alkyne? What we know now is that the cyclization should provide that intermediate. So why do we need more butyl lithium to do this beta elimination? Why doesn't it take place directly at this stage? So that question was also answered by calculation. We did first some experiments that I want to show you. We decided to start from this isolated intermediate that we obtained with one equivalent of butyl lithium, and isolated it cleanly, got this compound very clean and purified, and we decided to treat it with one equivalent of N-butyl lithium. Well, we don't know what happened at this stage, because when we quench this reaction, we just recover starting material. So it looks like one equivalent doesn't do anything. Quite unexpected also. So we decided to treat with two equivalents of N-butyl lithium, and in this case we obtained cleanly, with a very good yield, the expected product. So at least two equivalents were necessary. Why? Strange problem. We also noticed that if instead of using one equivalent of N-butyl lithium, we're using one equivalent of tertiobutyl lithium, the reaction would work nicely this time, 58% yield, it's okay. And of course, tertiobutyl lithium is a stronger base. We also noticed that if we were using only one equivalent of butyl lithium, but using one equivalent of HMPA in the medium, the reaction would proceed also very nicely. So it just suggested that maybe it was just a matter of activation. And indeed, when we warmed up the medium from minus 78 degrees to minus 40, this time the reaction worked with no HMPA, nothing. So it was just a matter of pushing the reaction a little bit further to get the elimination work. So why is that? Doesn't answer the question, does it? So we think that what is probably going on in this strong basic condition is that this position, which is not so acidic, but a little bit, because it's in alpha of the oxygen, and which is also allylic, gets deprotonated by insisting. So we get this intermediate, and probably a conjugated elimination takes place through these double bonds and gives the final product. So that's the hypothesis we have. Actually, we confirmed this hypothesis by calculation. We tried to do the beta elimination of the intermediate, and indeed, you can see that to get this alene, you need more than 15 kilocalories per mole. That's too high. You cannot do this reaction minus 78 degrees. It doesn't work. So you need a lot of energy to do it. We also tried to see if there could be a sigmatropic rearrangement between this methoxy and one proton on this position, but it's even worse. You see 22 kilocalories per mole. So that's impossible at minus 78 degrees. So these are not possible routes. So the third route we tried was to deprotonate this position and do this intermediate dilithio compound. And this dilithio compound, as soon as you make it, it transforms in this gem dilithio intermediate, no activation barrier. And you can imagine that such a species will evolve very rapidly to eliminate a lithium methoxide. No activation barrier. So no activation barrier, no activation barrier. Now the reaction is very, very quick, of course, and the beta elimination is instantaneous to give the final product. So we probably did an excess of base because we need to do a second deprotonation on this intermediate and deprotonate this position now to get the beta elimination work. All right, so that makes things a little bit more clear. It explains why we need an excess of base. But still, why is the situation so different between triple bond and allenes? Well, let me just summarize what I've shown you. Triple bonds, we go to this cyclization, we obtain this product, and to do the elimination, remember, more than 15 kilocalories per mole are needed. Very high barrier. While with allene, reaction takes place, and the elimination takes place with only less than 1 kilocalorie per mole. Very easy, so the elimination would take place immediately. So why is there such a big difference between this situation and this situation? Oh, the answer, I guess, is very easy. You can imagine yourself. It's just because this carbon is sp2, and so the elimination here to generate a second sp2 carbon is just too much strength on one carbon, while here, carbon sp3 elimination is very easy. You just generate a new sp2 bond. Nothing special. So no tension, no strength. The reaction is very quick.